So welcome to ECEN 215, Principles of Electrical Engineering. Today's topic is an introduction to microcontrollers. This is our last topic in ECEN 215. So this again is a topic in which primarily is informational. There will be some questions on the test regarding maybe some of the questions and some of the points that are brought up. But overall, this is meant to be a lecture to provide you content information that you could use later in your career. Today, being such a digital world and everything being connected, through the internet and databases and sensor systems and basically what we call IoT, which is the Internet of Things, and how sensors are connected to pretty much everything we do and the computational decisions are made. We have become a very, as we would call it, an embedded systems society. Whereas 30 years ago, it was very uncommon to find an embedded system in some general systems. Nowadays, it's just commonplace. Your thermostat has an embedded system. Your air conditioner has an embedded system in it. You use embedded systems if your vehicle has an embedded system. Your watch is an embedded system if it's like a smart watch, your phone, so on and so forth. Everything has some sort of a microcomputing device making decisions based upon sensor inputs. And so regardless of what discipline you're in, you're more than likely going to come across the need of working with a version of a microcontroller. And so that's why we have this emphasis at this point in the class, is so that you can understand how that's going to interface you, and in basically when and if you really do have to use one, kind of some of the basics and background of that. So the outline of this lecture is just a general introduction to what microcontrollers are. One of the most common points that you're going to be stuck on as an engineer, if you have to decide on a microcontroller, is what kind of microcontroller to use, how to best select and fit the microcontroller to the solution that you're using. Also, just some basics of microcontrollers, things to look out for. And then obviously one of the biggest things is deciding whether to use an embedded operating system like embedded Linux or using bare metal. This is a very common question that a lot of students have, and whether or not, and what that means, and whether or not that applies to your particular problem and solution that you have to come up with. And then, of course, some of the common pitfalls that engineers make when they're using microcontrollers. So what is a microcontroller? Microcontroller is MCU is a microcontroller unit. It is really a small computer on a single integrated circuit. So you've seen us talk about op amps and the little circuits for an op amp, a little 8-pin package that's an integrated circuit. You can actually get a full-blown microcomputer that you can write code for, read signals coming in the pins inside of an 8-pin package. In fact, I've actually have seen microcontrollers in 6-pin packages. They're completely programmable, and they exist to do some very simplistic functions, but they are full up little small computers. They have RAM, they have ROM, which means a read-only memory and random access memory, and they have various peripherals to interface the outside world. The common peripherals are digital I/O, in other words, be able to turn on and off signals. If you remember in the previous lecture we had on transistors, and we talked about turning on and off an LED, well, you would actually use a digital I/O port to do that, or controlling a solenoid valve, for instance, making intelligent decisions, so to speak, of when to control something. A UART, what stands for Universal Asynchronous Receiver Transmitter, is what we know affectionately as the serial port. You may or not have seen this so far in your studies, but a serial port is very common in industrial circles. It's just a way of transmitting simple data to and from one computing system or sensor system to another. And then obviously there are devices dealing with the analog world, because in the end, sensors are usually an analog device, and so you're needing to get that information into the microcontroller to make an intelligent decision that you can do programmatically. And so you do that by using an analog to digital converter, ADC for short, and there are different resolutions and different speeds, but actually ADCs are quite common to be as a common peripheral built in to the single IC of a microcontroller. Same thing with a digital analog converter to go any other way, having a numerical value that you compute and then wanting to convert that over back into an analog voltage to be maybe sent over to a sensor or amplified over to some sort of a servo motor or something like that, some sort of an output device. So actually, all of this right here, I was mentioning a moment ago, using an 8-bit microcontroller. And I was just using one the other day for a simple project. And actually, that single chip, small 8-pin, literally the same package that an operational amplifier was in, the same physical package. It had digital I/O, it had serial ports, and it had both an analog and a digital converter. It supported these communication protocols named SPI, serial peripheral interface, and I2C. This is another. These are just communications technologies for going from chip to chip. So you can actually interface more analog digital converters and the like. And then we also have timers and pulse width modulation. If you remember from the lecture the other day on transistors, where I introduced pulse width modulation, most peripherals inside a microcontroller unit can support pulse width modulation. So you can do motor control where you're using pulse width modulation as a method for doing that control, or heaters, or etc., as we were talking about in that part of the lecture. So these are very common peripherals in pretty much every microcontroller that you can purchase today. So microcontrollers got their start effectively in the late 1970s and actually about 1980. In fact, the very first microcontroller that's considered today, kind of comes along between Intel and, we'll see in a minute, Microchip. Intel, for instance, the Intel 8051 family was a very popular microcontroller for probably about 25 years. Through the 1980s, through the 1990s, and even into the early 2000s, this was a very common microcontroller. It is used in a lot of industrial applications. It started out its life before it was known as the Intel 8051 as the 8048, which was actually a microcontroller that was part of the first keyboard for the first IBM PC. So the first IBM PC had a keyboard, and they actually put a microprocessor solution inside the keyboard to do nothing but read the keys of the keyboard and transmit the character to the actual microprocessor that you were programming. So, like I said, this became the first major microcontroller. It only had 128 bytes of RAM, only 128 bytes. That's not kilobytes, that's not megabytes, that's not terabytes, not gigabytes. It is bytes of RAM and only 4 kilobytes of ROM. So this thing had practically nothing for storage. Usually when I give this lecture for my senior design students, usually this is a refresher of microcontrollers for them, they're usually shocked by this because we have gotten used to now having programs that we can write on our computers that take up megabytes and gigabytes of space. When you actually had to program for the 8051, you had to become very creative in your use of variables and storage of your subroutines and what you were doing. And I've actually cut my teeth, so to speak, as an embedded systems engineer using the Intel 8051 family. So you got really creative coming up with solutions. I've done some complex systems with Intel 8051s, but you had to take certain liberties and certain shortcuts. You learn some interesting mathematics to try to get around some of the limitations. Doing floating point math, for instance, with an 8051 is kind of a no-go because there's no point, but you can find some shortcuts around that. It used 12 clock cycles per instruction. So a clock cycle, again, is an oscillation that we've seen before. It's a digital signal. And so when we think of clock cycles, for instance, for your probably Intel Mac, for instance, your Mac OS, or an IBM PC, laptop, usually you're talking something in the neighborhood of a couple of gigahertz. For instance, the computer that I'm using here runs at 4 gigahertz. Well, reality is this thing used to run at 12 megahertz. So this thing was really slow and used 12 clock cycles. So of that 12 megahertz, you would then divide by 12 and you would actually get 1 million instructions per second through this processor. It originally only had one UART, just one, so one way to communicate, and 2 simple timers. as the years went by, they improved the 8051, and then of course the 8051 sprawled into various different families, and a couple of copycats, basically a couple other companies copied the design and then expanded its memory capability and speed and added a host of peripherals. The microchip PIC, known as the peripheral interface controller, this originally dates back to the 1970s kind of as well. It started out again as a peripheral device for a lot of the mini computers, specifically the DEC mini computers of the 1970s. The advantage that these have, I'd say, over the Intel 8051 and a lot of other microcontrollers, PICs are typically very easy to use. I've actually have taught embedded systems in an afternoon for a lot of students and other engineers because effectively, if you can download the tools, I can pretty much get you up and running with a PIC in probably 30 minutes. Essentially, apply power. You hook up the programming pod to it, write a simple program, and you could be blinking an LED literally within minutes with a PIC. They are very easy to use. They have built-in oscillators, so you don't even have to worry about dealing with an external clock or having a way of, or a crystal to actually get these things to respond. They are very robust. I have used microchip PICs and kind of some of their similar cousins for pretty much the last going on 30 years. And this family of PICs are very slow. They do have limited peripherals, some of the early PICs, but they are extremely robust. And typically, I can have system applications returned from the field damaged for whatever reason, usually lightning. The processing solution is usually still fine. Usually some other circuit that gets damaged. Microchip PICs are very, very capable. They have everything again down to the 8-pin package all the way to larger 32-bit systems. Very fast, very full of peripherals. In fact, I use a lot of what's known as the PIC32 family, and now Microchip owns the Atmel family as well. And there's a lot of ARM-based microcontrollers, and the Microchip family is very, very versed in capability, which really gets us to also now talking about single board computers. So this is obviously includes things like Raspberry Pis, Arduinos, things like this. Raspberry Pis is something you probably already familiar with. Most high school students nowadays already kind of play around with Raspberry Pis. You can use a Raspberry Pi, and if this is something like if you're into mechanical engineering or whatever, and you're trying to just literally, I just need something to hook up a servo or read a sensor, you can hook up a Raspberry Pi and within moments start collecting data, writing code in Python and doing actual analysis using Python as your platform. I think you can even use MATLAB on the Raspberry Pi. So, I mean, you can really do some pretty creative concepts using a Raspberry Pi or similar platforms. So there's a Raspberry Pi, there's the Banana Pi, there is, which I highly, it's kind of a mixed unit. The Raspberry Pi, I think, is better versus that. There's the Odroid family, which that's actually I consider better than the Raspberry Pi, and there's a variety of others. So if you type in single board computer at a Google prompt, you will be flooded with a reply. In fact, there's a Wikipedia page that's available that lists and grades a lot of single board computers. The main limitation of Raspberry Pis is that they are great for proof of concept or hobbyist platform or doing something in a lab, just trying to get some answers really quick. Raspberry Pis are technically an educational product. As such, they get an educational grant, and you really can't use a Raspberry Pi in a product. And the reason I emphasize that here is I have a lot of clients that I've gotten over the years that will call up and say, we've got a complete solution. We just want to mass produce this system. And if you dig into their system, they're actually using a Raspberry Pi as their main microcontroller solution. Perfectly fine for a prototype, so to speak, and kind of proof of concept, but you can't go to production for that. There's also a bunch of field programmable gate arrays, as they're known, FPGAs with ARM processors, known as the Zinc family. That's a single board computer. This is a real popular solution if you're doing a lot of high performance computing, a lot of number crunching, and you just need raw performance. The Xilinx FPGAs are really popular for that. Probably not something that for the average, where you're just trying to do strain gauge measurements and temperatures and make some decisions, probably not the way to go. But if you start really getting in a lot of computational fluid dynamics and things like that that are real time, you might want to consider something like this. So there is a host of single board computers, and a lot of them are available for commercial use. One family, for instance, Toradex, is a commercial, totally viable, very high performance single board computer used in a lot of commercial applications and industrial applications, well priced, and really have wonderful industrial temperature specs and very reliable and can withstand a lot of punishment itself. So the big question is do you need a microcontroller for your project? So eventually, almost all of you engineering students in 215 here are going to be in part of a senior design project. I teach the electrical engineering version of senior design, and so usually the answer to this question almost immediately is yes. I have a few students that think the answer is no, but in reality it is yes. Now, in your projects, that's probably an open question. Because if it's purely mechanical, there's actually going to be no way you're going to do any verifications with any microcontrollers or feedback circuits or strain gauges or temperatures going back to a computer, then the answer may truly be no. But if you sit and think about your project, you're probably going to answer yes in some form. Now, in your solution, it might be that we're going to hook up my laptop to it, and I'm going to have a whole suite of sensors hooked up, and that's perfectly fine. But if you're going to have anything where you're going to have a system that's deployed, you're probably going to have an embedded system as part of that. Now, that embedded system might be simply just a Raspberry Pi with a bunch of sensors hooked up to it, and that technically is a microcontroller solution for your project. So the things you need to be asking yourself while you're making this decision is if your project needs a microcontroller, is do you need to do any system processing or make any control decisions? Do I need to turn on and off a motor at some point given a condition? Do I need to turn on and off a heater? I'm going to be controlling temperature in some sort of a PID system, process, instrumentation diagram, basically a piping and instrumentation diagram. Do I need to control a vat of fluid at a specific temperature? Do I need to raise the pressure of this vessel to a certain PSI? Do I need 50 PSI to be maintained at all times? Beyond just using a simple pressure regulator, I've got to make active decisions like controlling a pump and so on and so forth. If you're doing any type of processing, you will likely have a microcontroller. Do you need to communicate any of that data or have user interaction? Do you have to have a user specify a temperature range? Do you need to have them interact with the device that you're building for whatever reason? If that is the case, then you're communicating with the user, and the answer is yes. Or if you're communicating that data, for instance, via Ethernet, or over the internet to a remote site or something, then yes, you're more than likely going to need a microcontroller, because if you're going to commute that data, you're going to transform it from one form to another, and you're going to transform it to something that can be broadcast over the internet into a packet, then yes. Do you need to communicate with other systems? One of the common protocols, you probably have never seen this before, something called Modbus. This is a very common industrial protocol that's used on a lot of programmable logic controllers, PLCs, and you will most definitely, if you're in mechanical and civil engineering, etc., you probably are going to encounter PLCs at some point or another. And so this is a common technology that and Ethernet are going to be communication. In fact, almost all three of these technologies are heavily used in PLCs. And if you've used a PLC, you've used a microcontroller. So what kind of microcontroller do you need? This is a part where you can spend many, many, many long hours. And this is where I usually emphasize writing requirements and writing your specification for your project is the number one thing you need to do here, because you can really get a case of featureitis in your project really bad. I usually tell a story where when I'm trying to share why you need to write a requirements and specification document. When I was working on a product about 20 years ago and I was going back and forth on the microcontroller selection, I had a set specifications for the product, but I kept looking at one microcontroller and I was like, ooh, these features are pretty cool. And I'm going to add those features of this microcontroller to my design. Even though I didn't really need those features, they looked cool, so I added it to the features list. As I started designing the project, I realized that some of the core pieces of information, the core ingredients that I needed the microcontroller to do, it didn't do. But then I got into a point where I really liked those cool new features. And so I got featureitis, and I kept going back and forth between my requirements document and my what microcontroller selection. I ended up spending in the end 3 weeks, I kid you not, 3 weeks going back and forth between microcontroller and specifications and not letting the project drive that decision. If I would have just let the project drive the decision, I would have had us settled on one microcontroller early on and been done and been the market faster. So again, I usually have this in here for my senior design students. Don't just assume that a Raspberry Pi will be the solution. The reason why is a lot of them just assume that and just buy one immediately because they're $40 and they're pretty easy to get. They're easy to program. The problem is that there are limitations to what you're trying to do with a Raspberry Pi. You have to look at special things. You have to ask yourself, what are you doing with your microcontroller? Am I interfacing with an A to D converter? Am I trying to get sensor data out of that microcontroller or into that microcontroller from something? If it's really slow, like temperature or pressure, where the changes are, at best slow hertz, 10 hertz, 5 hertz, then probably almost anything you throw at it will work fine. However, you're trying to do image processing and use a camera, and you're going to want to do frame like you're using a high-speed camera, like you're working on, say, an assembly line, and you're building the mechanical system to actually to drive an assembly line that's running at full speed. You're probably going to, in that case, need a high-speed camera that's running at 800 frames per second. In which case, it means your microcontroller, to make an intelligent decisions and do the image processing, needs to be able to receive 800 frames per second. If you ever do the computation on how many pixels per second that is, that's a lot. And so that your average microcontroller probably will not do that. And how you communicate that camera data to the microcontroller also matters. And so there's a lot of things that have to be taken into account there. How fast are you going to communicate? I only need to send occasional data here and there, like settings and user input. That's one thing. I need to move data, like I was talking about the images, back and forth between the microcontroller and, say, a database somewhere. In that case, you probably are going to need megabits per second or maybe even gigabits. So what are you doing there? How many digital I/O you need? This all comes down to, in the end, coming up with your requirements and specifications. I will add that more than likely as your engineering studies, you probably have not had, unless you're like in industrial engineering or something, you probably haven't had a systems engineering class. I would highly recommend taking a systems engineering class as an elective if it's not required for your degree plan, because learning how to do requirements and specification documents is going to be something you're going to learn anyway on the job. And maybe having some formal education there would probably be helpful, because this right here drives a lot of these kind of things, and it also drives everything you're doing in your actual discipline. Microcontroller selection. This is continuing on. I mean, from there, you're now starting getting into manufacturer selection. Am I going to use Microchip? Am I going to use Texas Instruments? Am I going to be using Atmel? Am I going to be using Xilinx? So on and so forth. NXP. Um, a lot of that you're probably not going to have to worry with. Probably whoever engineer you're working with on your team is probably going to be deciding that. A lot of the manufacturer stuff comes down to, in the end, how comfortable of an engineer you are with a certain brand. There's a lot of brand loyalty in microcontrollers, and a lot of that has to do with the fact that once you learn tools for a certain microcontroller, you tend to want to favor that microcontroller, because no one likes to have to relearn their tool sets and learn all the quirks and features of another microcontroller. When I first got into embedded systems, 25 years ago, I got lucky that I landed with a company that made tools, made compilers. So I got to experience working with a variety of different microcontrollers and all of the quirks and features. Sort of got used to dealing with change a lot. Typically, I run into companies and they line up on, like, we're going to do everything with Microchip. We don't care whether or not it fits or not. We're using Microchip. So again, it just really depends on you. The size of the core, 8-bit, 16-bit, 32-bit, 64-bit, etc. This really depends on the technology. If you're coming up with something where all you're doing is controlling a temperature or controlling a valve, turning on and off a heater, for instance, on the temperature, you probably can get by with an 8-bit controller. Something simple. You can probably get by with an 8-bit microcontroller. The advantage of the lower bit family is that they're usually more reliable and they're slow, but they're going to be more reliable. They're guaranteed to work. So you're going to have more reliability this way. I mean, throwing a 32-bit or 64-bit ARM solution running at 2 gigahertz just to turn on and off a heater is kind of foolhardy. It'll do it, but you also now have to consider, do you want to run Linux, just to turn on and off a heater? That's a little crazy, but I have seen weird things like that. And the number of cores with microcontrollers, just like with your processor and your laptop, you can have multiple cores. One of the systems I'm working on right now, it's an NXP microcontroller. It supports 4 separate microcontrollers actually inside the one master controller. In other words, it's 4 ARM cores. Um, so that's something to always consider. So it brings you more ability to processing. A lot of this here just has to deal with the fact that how much memory you need. Do you need internal, external memory? If you're not doing many variables, you're making light computations, I would just focus on the internal memory. If you're doing a lot of video processing, image processing, um, 3D analysis of a LiDAR cloud or something, the LiDAR being a 3D point cloud technology, you're probably going to have external memory, because you're actually dealing with gigabytes and maybe even terabytes of data. So this all becomes very important in your selection. Then you always have to consider the amount of I/O pins. Always err on the side of more pins is better. Don't just choose the number of I/O pins to match your particular solution. So if you have 10 I/O pins is all you need, look for a device that maybe has 20. Because you might be, as you're redesigning your system, you might want to have a few more I/O pins. Peripherals to consider: analog digital converters, digital analog converters, timers, pulse width modulation, capture compare, and communications. All this means is this for capture compare. This is usually dealing with time, pulses basically coming in. Communications, for instance, we were talking a moment ago about UARTs and Ethernet. What do you need? So you want to make sure that your microcontroller supports the actual communication interfaces that your system will actually need. What kind of storage do you have? Do you need non-volatile storage? You're going to need some. You're going to want to stick the program. You don't want to have to reload the program every time from RAM, reprogram it every time. So it's going to be stored in something called flash. But you're also going to have settings and characteristics, calibration points. All that needs to be stored. When you turn off the power, that is known as volatile storage. If you turn off the power on RAM, it loses its contents. So you need to have a non-volatile storage solution to maintain things that will never go away. So when the power comes back on, it instantly has that old information. Do you need graphic processing units? Again, if you're doing image processing or video processing, more than likely. What type of oscillators? And the big one here, operating temperature. Always consider this whenever you're building a solution. I know I've mentioned this several times with like transistors and things like this. Operating temperature is key. You don't want to design a microcontroller solution that is only good for commercial temperatures, but it's going to be an industrial temperature solution. In other words, something that's rated for 0 to 70 is fantastic at room temperature, but it's not going to work very well if it's exposed to minus 50 degrees Celsius. It's going to be out of tolerance. Same thing, if you got something that supports up to 70 degrees Celsius and you end up working in an environment that's pushing 80, 85, 105 Celsius, which does happen. Think automotive. That becomes a big problem. Package, case, and type. If you're dealing with microcontrollers, this again is mostly aimed to my senior design students. If you're actually going to be building, you need to consider what the type of package is. Everything we've seen, like with op amps and stuff, we're dealing with DIPs, dual inline pin, SOPs, single outline pin. This is a surface mount package. These are fairly easy to solder. In fact, DIPs are extremely easy to solder and actually use on a breadboard. Ball grid array, BGA, is not something you hand solder. It is done at the professional level, done in the assembly shop. Don't be one of these students who end up choosing a BGA package for their senior design project and wonder why we can't do anything with it. You're not going to be able to solder this on the board. Basics. So now that you've picked a microcontroller and hopefully it meets all of your specs and requirements, one of the key things here is not to think you're the world's best programmer and write everything in assembly language. Again, probably for my 215 students, this is not going to be really that big a deal because you're probably wondering what in the heck is assembly language. Assembly language is the language of actually the processor itself. It's the machine code. It is just an English language version of mnemonics of the actual command language of the processor, instruction by instruction inside the actual microcontroller, what it actually executes. My 350 students, so if I'm talking to my senior design students, you've all had ECEN 350, and you're kind of had to learn some assembly language to get through the class. Please do not think you need to write assembly language. We have really good compilers today that will take the language of C, C++, or Python or Java and are able to make that work for your microcontrollers. Predominantly for most microcontrollers, C and C++ is the default language for the most part. In fact, I do a lot of embedded systems. I probably work on 20 to 30 embedded systems a year. I predominantly work in the language of C. Again, most single board computers, again, your Raspberry Pis and things like that, you're probably going to be writing in Python a lot for those and or Java. So, just kind of depends on the platform. You want to make sure that any code that you do write, you test each section separately. Make sure that you do not write all the code at once, like main.c, put all your code in, every little bit, every little detail, and have never tested a single line of it until the day everything shows up and you want to test, and you test the entire thing. You will spend your next probably 2 months in development hell. You want to make sure that you test each section separately. Write what's called structured code, which means you want to write code such that the A to D converter has its own separate subroutine. The D to A converter has its own separate subroutine, and you can independently test each part. You want to test each peripheral separately, such that when you get to the main functions, maybe making some intelligent control decisions, the actual lines of code to actually do that are very short and simple, and those can be independently tested as well, such that when you combine everything together, all of those independent pieces are tested separately, so you can feel reliable that this should work because everything individually worked, and it's just usually high level stuff that's just some silliness that you got to fix. You want to use something known as GitHub, which is a repository for storing your code that you write. Of course, you can either use version control like SVS, Subversion. There's probably about a dozen different version control utilities. I highly recommend using something like GitHub to keep your firmware, which is the code that goes inside your microcontroller, organized. Do not be the student that usually happens this again, a more of my senior design students, that when you get to the part where you actually have your firmware written and are in the process and you do not make backups, do not be the student that calls up at the end of the semester going, Dr. Lusher, I hate to tell you this, but I don't have anything for my project because my computer died, or my battery died, or my hard drive crashed. Those things do happen. You need to back up, and this is an excellent way of backing up your code for your project. But this goes for everything, and this is for all students here. Make sure you back up everything you do. Hard drive crashes do happen. In my roughly 30 years of being in the industry, in that time I have experienced probably about 4 hard drive crashes. I've come in many a times where my computer is just sitting there blinking, hard drive not found, please insert boot media. Those are the phrases you do not like seeing when you walk in your office at 6 or 7 in the morning, because you may have a very long, nasty day ahead of you. If you back everything up on multiple drives, I'm a backup king. I like to back up to external drives. I back up to offsite. I back up over the internet. I use Google Drive. You name it, I've got it backed up. I rest comfortably knowing that the files that I had 25 years ago are still being maintained to this day. So if I need to go look up a project that I did in 1999, which I actually do on occasion, I can actually go and look at that information. And if I walked in tomorrow and my computer blew up, it'll be a bad day. I have to replace it and get everything fixed and go through. I'll lose time, but I'm not going to lose the information. It sounds easy to do, but believe it or not, pretty much at least every 2 semesters, and I just had one last semester, this happens. Someone actually does. And this is not a made-up story. This happens routinely. So don't be that student, please. So learn from others before you. Check forums, example code, previous projects, etc. This is really important. And this is all students, senior design, 215, you name it. This is true. You as engineers, you are going to be entering the workforce. You are not doing anything that hasn't been done before. Very rarely that happens. You might be innovating something new. You might be pushing the outside of the technology envelope in some form. But in a way, a lot of the stuff you're doing, you're learning from others, and you're expanding upon that. and you're trying to build something. I think I read the other day a great phrase: um, scientists build to learn, and engineers learn to build. That seemed like a very good phrase, because we both learn and we both enjoy learning things. But as engineers, we're all about building stuff. That's why I became an engineer. I just loved building things. And so because of that, always look for what other people have done. Don't go into your first job and think you need to be the one who solves this particular problem. As an engineering manager in the past, I have seen junior engineers come in a company, and I have actually assigned them a project and say, here, figure this out. And they'll spend a week or two on something when all they had to do was talk to their basically effectively a cubicle mate, the person has been there for 15, 20 years, and they would have just asked for help. The problem would have been probably fixed within a day, but they spent 2 or 3 weeks trying to figure it out because they wanted to make an impression. Well, they ended up causing a lot of overhead doing that. In a way, it's a test to kind of build up this example. Always learn from others. So you want to make sure it's good to learn on your own, learn those new things, but you also don't want to just waste your time either. So make sure if you have a problem and you're trying to figure out some microcontroller peripheral device, instead of spending hours upon hours reading the user manual, it might be good just to go on the forums and ask, hey, I'm trying to use the A to D converter on this microcontroller. Is there an example project I can look at? 9 times out of 10, I'd say 99 times out of 100, there is. Learn your integrated design environment, IDE. Learn your IDE. And this is true with any tool for that matter. I mean, if you're using SolidWorks, learn SolidWorks. If you're using AutoCAD, use AutoCAD. If you're learning to use Altium, which is the one we use for printed circuit board design, or pads, whatever it is, make sure you learn your tools. Because there's nothing more frustrating than trying to stumble through a project and you really don't know how to use your own tools because you're going to miss certain things. So it's always good, take a couple tutorials, take a few hours, do a few tutorials to learn how to use your actual device. Again, test all your major subsystems like your your ADC, and your DAC. A lot of microcontrollers have an integrated debugger, which this is really good because um, this is something that's kind of fairly new. And I say new, probably that's been in the last 20 years or so. Debuggers used not to be integrated in a microcontroller, and so you had to come up with creative solutions to even know if your device was operating correctly, beyond just the fact that it's doing exactly what's supposed to be doing right out of the gate. So debugging a system used to be a long, drawn-out process. Nowadays, you can do things called watch variables, where you can actually stop a microcontroller, read the variable contents right then and there. You can put stop points. You can put all sorts of conditions on a microcontroller, which is very useful. This is all now built into almost every microcontroller. So please make sure you use that if you're doing microcontroller design. You need to plan for any extra I/O and performance. This is something that people, again, lack and don't do. They go exactly off the requirements. I need 10 I/O lines, 2 A to D lines, and 1 D to A, and they get exactly that. And inevitably, if you are an engineer and you work for an R&D company, well, the research part of that, you're a research scientist, it's research. They don't know exactly what they're doing. So they're working on the bench. Adding another temperature sensor and a process diagram is no big deal to them. They just add another thing to their LabVIEW setup. It can support another I/O. To them, it's fine. If you're building a dedicated product, adding additional I/O can become a bit of a headache. I mean, you got to plan for extra connectors, you got to plan for the actual electronics, so on and so forth. You got to make room for it in the algorithm. If you go ahead and make that plan ahead of time, when the research scientist comes up to you with you and tells you they have another temperature sensor they've added in, you can just smile and say, okay, instead of like, oh great, there goes 6 weeks of work down the tubes. Use a thing known as a watchdog timer. A watchdog timer is basically a reset circuit that is built into a microcontroller, and it's typically part of the microcontroller electronics. And it usually is a timer that is strictly there to do nothing but reset if you do not reset it. And you go, what's the point of that? Well, if you have a very complicated microcontroller with a lot of really complicated instructions, so a complicated program, and something doesn't go right, you didn't get some information correctly, the communication locked up, lightning was nearby and actually caused the processor to jump in its program counter, and it's in the wrong, in other words, it just completely loses it. So what you want to do is make sure that you have this device called a watchdog timer. And what you do is you pet the dog, you reset the watchdog periodically inside your program. If your program does not reset the watchdog timer, the watchdog will eventually reset you, such that if you happen to be computing the wrong point on something and it just kind of loses its, my processor loses its mind, usually within 100 milliseconds, the watchdog timer resets you, and at least now your processor goes back to a known state. Watchdog timers can save industrial applications a lot of grief, especially man-rated systems. You got to be very careful to make sure you use a watchdog timer. When you leave out the WDT, which is an easy thing to do because you don't have to deal with resetting it, and it's fine in a debug environment or a design and development environment, but when you go to releasing a product, you want to make sure this is installed and working. So comment your code. So at the end of the day, you're going to write some code for your microcontroller. Please use good commenting skills. And this is aimed at everybody. Senior design, my mechanical engineering students, my aero unit students, my electrical engineering students, all of you, please comment your code. No matter what, you're going to be writing code no matter what you do, no matter what your discipline is. You'll be writing something in Python, MATLAB, I don't care, Java, writing code for some HTML portal, some website portal. You're going to write code at some point in your career. I can almost guarantee it. Please comment, because in the end, someone's going to come behind you. You're going to leave that job, move on or something. Someone's going to inherit your code, and they need to read your mind. The only way we can read your mind is that you comment in it. Else it's going to get ditched and you'll be rebuilt. Use variables, use what we call self-documenting code or self-commenting code, and that's using things like variable names that actually mean something. If you've got a temperature sensor, don't use the variable X or var. And you would think that this is a joke. I have actually come behind firmware that actually uses X and var as variable names, and this is like pressure sensor X. Not the name X. I mean, they used X for the pressure sensor on like a casing pressure. Well, that doesn't tell me anything. X. I don't know what X is. I had to actually go back and look through the schematic and look at the PID diagram and figure out, oh, this is casing pressure. So when I rewrote the code, I actually called this casing pressure. Guess what? My computer has enough RAM and ROM and space on the hard drive that X versus casing pressure did not kill my hard drive. So please do that. Make sure you use structured programming, clean, nice, simple code blocks. Use a block diagram and flowcharts when possible. Always start out any project, no matter if it's a mechanical project or if it's an electrical project or it's just a system overall, which in the end, all of us are working together on a big project. Use a block diagram and describe the project. Have a document describing all code functions at a high level and list any dependencies. Odds are you're going to be using what's known as an application programming interface, basically this third-party interface to do some basic functions, especially if you're using something like embedded Linux. Make sure you list what that is so that if I'm coming back and figuring out your code in the future, we know what you used. And if we have to purchase something, we have to, but at least we know what it is. So embedded operating systems versus bare metal. So the whole point here is talking about whether bare metal just simply refers to the fact that I've got a microcontroller, I wrote every line of code, or otherwise am compiling every line of code that is going to be run on here. It is my responsibility as the embedded systems engineer on this particular project. An embedded operating system, on the other hand, does run some sort of operating system. It's running something like Linux or Android for that matter. Windows 10, Microsoft has gotten in the embedded game. Windows 10 IoT. There's various real-time operating systems, very time-sensitive applications. Noobs, this is something that's on the Raspberry Pi. That or Raspbian, for instance, which is a version of embedded Linux on Raspberry Pi. All of this is great. Embedded operating systems really offer a lot. In fact, most of your applications, probably embedded operating systems is perfectly ideal. If you're running something that requires a lot of control and you know exactly what's going on and reliability is an issue, embedded systems running bare metal might be better. So again, the advantages of embedded OS, you have a lot of rich built-in functions. All of the I/O for the most part already have existing drivers, which is fantastic. I don't have to write code for all the peripherals. It already exists. You have a ton of third-party tools that you can purchase and use, or it's already available for you, part of your license. You can run multiple applications at once, which is fantastic. If I have a really powerful microcontroller, I can do multiple things at the same time. It's common interface. If you're used to Linux, which if you're doing a lot of that, if you're doing a lot of high performance stuff and you're doing a lot of microcontrollers, you're probably going to involved in Linux. So if you're used to using Linux as an operating system, then you're going to understand the operating system of your microcontroller because it's exactly that. It's just an embedded version of Linux. Does provide a disconnect between the hardware and application code, which can be useful because it's an abstraction layer. It's one layer above. You don't have to worry about the A to D converter. It's just a layer of reading a signal. But the disadvantage is it does consume more processor resources, and your application layer is removed. So this is both an advantage and a disadvantage. The reason why that's a disadvantage is if you're trying to be very specific with your hardware and you got a very specific task, and like the example I gave earlier where we're just trying to turn and off and on and off a heater, and that's it, read a temperature and turn on and off a heater. If you have an embedded Linux application, so you got to boot Linux, I got to get all the peripheral drivers loaded, I got to do all this stuff. So there's so many layers that have to happen just to read a temperature. Whereas if this was a little 8-bit PIC, I just read one register and turn on and off one bit. I mean, yeah, basically I have this monstrous load of embedded Linux to end up doing what literally 4 lines of code do. Literally 4 lines of code on a microchip PIC is. So you got to weigh that, whether or not that makes sense in your particular product line. Bare metal, there is nothing between you and the application. That's a big advantage. You know exactly what's going on, just like in the case I just gave. There's no unknown code. Everything is under your control. You have complete source code control. You have very predictable performance because of that. It's usually a less complicated design. It's usually a one-chip solution or at least 1 or 2 chip solution. And it's an instant boot. You apply power. There might be a brief couple microseconds for a power boot up cycle, but other than that, immediately starts executing code. The disadvantage is you are now responsible for everything going on there. Which again, it's kind of the same thing. It's kind of an advantage and disadvantage. You're responsible though. So it all comes down to your particular code. All libraries and tools must be included in your firmware project. Again, it's advantageous. You know everything that's in there, but you have to have it. So common pitfalls, we'll just kind of wrap things up here. So not selecting the correct microcontroller based upon project needs, huge. This right here is probably the chief problem that I run into personally as an embedded systems engineer, is I will choose the wrong microcontroller based upon the requirements. That's why it's so critical to make sure you have a requirements document for the project you're working on. Making sure, one of the other common pitfalls is writing the full application without modular design. It just makes testing very complex. If you are designing this really complicated application, if you write all the code at once and try to test it all at once, you will run into problems. Not planning for extra resources like extra I/O or a debug communication port or something like that, you really need to be thinking ahead on that. You got to be thinking about how am I going to test what I'm building. Testing is, as a part of an engineer, is just part of life. I'm going to build and design something, but on the flip side, how do I verify what I design meets the requirements? There's something called the system engineering V model. There's a couple other system engineering models, but the V model is the one I follow. You enter the project based upon your requirements, and you leave the project based on validating those requirements. So it really comes down to your requirements document. Not using a debugger. This one bites a lot of my senior design students because they think they can use a Raspberry Pi with no debug support, and then they're trying to debug a really complicated firmware project. This really can come back and bite you big time. Wrong voltage or current on I/O pins. Again, a lot of this, I/O pins on the microcontroller at a certain voltage. Say it's 3.3 volts. If I try to connect a 12-volt device to my 3.3 volt I/O pin, 12 minus 3.0 divided by 0 is a problem. Ohm's law, but doesn't matter there. So making sure that we have the right voltages and currents being supported in I/O pin. You can't drive, usually drive a relay coil directly off a microcontroller. You can't push a couple hundred milliamps out of a relay coil. That's where you need to use a transistor. Not having enough memory. This is very common as well. Not planning ahead and going, hey, I need probably X megabytes of memory or X kilobytes of memory on an embedded system, or even X gigabytes. Thinking ahead is very important here, and make sure you pick the right microcontroller to do the right application. Having the wrong sample rate on your analog digital converters. So if I only need to read a temperature once a second, you pretty much, anything you throw at it is fine. But if I'm trying to sample a high-speed signal that's coming in at 10 megahertz, and I try sampling it with a 1 kilohertz A to D converter, not going to work. Not commenting your code and using a watchdog timer, that kind of goes without saying, and not planning any thermal design. Everything we're talking about, these microcontrollers do produce heat. They really do. Your Raspberry Pis do produce heat. So if you're planning a Raspberry Pi in a future project, make sure you buy the heatsink. By the way, they sell them for $40. It does not come with a heatsink. There's a reason for that, because heatsinks do cost a little more money. You're going to want to purchase the heatsink with it, because as soon as you start using the microcontroller, actually not just sitting there idle, but actually computing, it starts to heat up, and then it'll eventually, about mid-semester, this is especially true of senior design, about mid to late semester in 403, the senior design course, I will get a request to buy another Raspberry Pi because the Raspberry Pi died. Why did it die? It overheated. And last here, this is the really biggest pitfalls here, and this is true for any engineering project, is not asking for any help or advice. This is true for almost anything in life, honestly. If you just don't ask for help and advice, just ask for help. In case of college, ask your professors or TA for help. If you don't understand something, ask. Same thing applies to anything in engineering. You don't understand something, you don't understand a requirement from your client or a fellow engineer, ask. You need help figuring something out, ask. Please. It never hurts to ask. Please. And of course, making assumptions. And do not just assume certain conditions are going to exist. Don't just assume, for instance, the Raspberry Pi is the perfect solution as a microcontroller because, hey, it's $40 and I've been using it since high school and I know how to get it booted in about 5 minutes. That's an assumption. You don't really know if that's an ideal solution for your project or a product solution. Again, this is kind of a long together lecture going over all these different components. But again, this is just sort of give you a flavor of how you would use microcontrollers in your particular project and or product that you may be working on in the future. If you have questions or comments on this, please let me know. Like I said, I do a lot of embedded systems, so I can share a lot of advice. I can show you a lot of information on coding and structured programming. I will probably be sharing, especially to my senior design class, examples of how to comment and things like that. So if you want to learn more, please come to any Q&A session, and otherwise have a wonderful day. Thank you.